Having seen a few examples already of related rates problems, it's time to think about what kind of generalizations we can make. One very common element of these related rates problems is to draw a picture. If at all possible, try to draw some kind of diagram of the situation, labeling all the relevant variables. Figure out which variables and rates of change you know, figure out which ones you want. That's going to be your guideline for what things you're going to tie together through equations. And then look for such an equation where you've got the changing variables and including the one that has a variable, the variable that's whose rate you want to know. Once you have that rate, that equation that's always true, you can apply implicit differentiation before substituting in any known values. That's the most common mistake made by students when they're starting these, is to sub in too early. Take an equation that's always true, differentiate that, and then sub in the known variables and rates to solve for what you want. Now, this is a calculus course, and for whatever historical reasons, ladders sliding down walls have become the emblem, the poster child of related rates problems. So we'll do one here, just so we feel like we've all had the experience. Okay, a 5-meter ladder is propped up against the wall. You climbed up to the top, and then it starts to slip. Okay, so it's propped against the wall, and it's 5 meters long, so this distance is 5. The tip of the ladder is moving downwards at 1 meter per second. So it starts here, and then it's moving down at 1 meter per second. Find the rate at which the bottom end, if the top is going down, the bottom end must be kicking out, and find out at what rate it's moving, the bottom is moving. And we'll do it at 2 different points. Well, I think the most natural variable choice here is to call this x and this y. And once again, like our other example earlier, we can use Pythagoras to help present what's always true. The ladder is always 5 meters long, and so whatever the distance along the y side here is, how high the tip is, it's going to be balanced by how far away from the wall it is using Pythagoras. Okay, what do we want? We want to know at the rate at which the bottom end of the ladder is sliding, and that's dx dt. What do we know? We definitely know dy dt, and it's 1 meter per second. And you just have to be a little careful with signs. If y is the height from here to here, then if y is going down, the tip of the ladder is sliding down the wall, y is actually decreasing, so we'd have a negative rate. dy dt will be -1. Okay, so now we have an equation that's always true, a few things that we know and that we want. Now we're going to take the derivative with respect to time of both x squared plus y squared, the left side, and do the same thing on the right. So we're taking time derivatives because we're interested in rates of change, and these natural units for that in this case here would be meters per second. One easy derivative on the left, or on the right rather, derivative of 25. On the left, remember, this is not a classic implicit derivative. This is the derivative with respect to time of x. So we'll get 2x times the derivative of x with respect to time. And exactly in parallel with that, we'll get the y derivative with respect to time on this side. So these rates are related through this equation, and so we can find out that dy dt, actually no, we want dx dt, or we want dx dt. Dx dt will bring everything to the other side, so we'll have 2x is equal to 2y negative dy dt, and then we can divide by the 2x and get that. That would be our relationship between the rate that we know, the tip of the ladder sliding down the wall, and the rate we want, the rate at which the bottom of the ladder is being kicked out. We'll now consider the two cases. What is that rate when the bottom of the ladder is 3 meters away from the wall, the bottom 3 meters away, and when the top of the ladder actually hits the ground? We'll do that on the next page. So if dx dt is negative 2y over 2x, we could certainly cancel the 2's to save ourselves some time. And the first example was the bottom 3 meters from the wall. So here, going back to our trusty diagram, we have our ladder. It's 5 meters long. This length here, we're going to have it 3. That's our x value. And because this is a 3, 4, 5 triangle, that's the only number that'll, 4 is the only number that'll fit there. Our y coordinate, our y value will be 4. And we can simply sub in here. We also have dy dt, which is the speed at which the tip of the ladder is moving downwards, was negative 1 meter per second. So for A, we're going to have dx dt is equal to minus y, which is 4, over x, which is 3, times negative 1, which is dy dt. And we get 4/3 meters per second. And we note that this is a positive value, so x is increasing, and that makes sense. If the tip is going down, the bottom is going out, and we get a positive rate, 4/3 meters per second. There was a second point we were interested in, though, which is when the tip hit the ground. This is not going to look like much of a diagram because the ladder is going to be flat. It's going to be 5 meters straight along here because y is going to equal 0. And so x must equal 5. Under that scenario, dx dt will equal minus y. Well, y is 0 over 5x times the negative 1, which is the rate at which the ladder was decreasing at that moment. And then we just get 0. So think about that for a second. Does that make any sense? When the tip hits the ground, the bottom is not moving out anymore or in. It might seem surprising at first, but it actually makes perfect sense. Imagine the ladder sliding down and down and down. When the tip hits the ground, the ladder's not going to move any further out. In other words, x is never going to go larger than 5. It can't because the ladder is just 5 meters and it's going to stop. And it's also not going to get any closer. It can't be any, x can't shrink because at the moment this is hitting the ground, the whole ladder is laid out. It's 5 meters long. There's no reason for it to contract. So in fact, it might be a bit surprising to think, when the tip hits the ground is exactly when when the bottom stops moving. Another way to think about that is if you were a person standing here, this ladder's falling down, would you feel safe with your foot 5.1 meters away from the end? Of course you would, because as the ladder slides down and down and down, it's going to get perfectly flatly stretched out, and it's going to stop at that moment. This bottom is not going to move towards you any further. How would we say that? The rate of change of x will be 0.